Hey guys, happy halfway mark through this week. We are looking at passive transport and homeostatic regulation. This is really where we're going to be taking everything that we've talked about so far this unit and put it into one. And a couple of things that I want to mention that came up in the survey. So first of all, don't worry about a test. We're not going to be doing any tests. Your Unit 4 assessment is going to count as the assessment or the test for this. So you have some options on how you want to show what you've learned. So again, if you're like, hey, what do I need to know? Go back and look through that. And as long as you can do one of the assignments for each topic that we're covering, then you'll be good to go. Okay, so I hopefully will be able to go quickly through this. Your assignment today is going to be to just skim through the chapter, and there's going to be some things that you're looking for from chapter 4.3. So we're looking at passive transport. Yesterday's video already went into a little bit of detail about molecular movement and the movement of things from a higher to a lower concentration, usually solutes, but today we're actually going to look solvents as well. So I'm going to give you a quick overview of this chapter. That way you have quite a bit of context, and then you're not going to have too much note-taking to do. Maybe 10 minutes or so per chapter or per section should be all that you need. Sorry, I'm joking a little bit. And what you're going to look at is diffusion, and more specifically how it's applied, facilitated diffusion, and how it's applied, and osmosis. So for each of the sections, what you're going to need to do is scan through the section. For example, chapter 4.3.2 deals with oxygen regulation. And so the way that these are organized is to take a little bit of information about how materials cross the membrane and then put them into context into an applicable example. So for example, with diffusion, oxygen is going to be one of the types of molecules that can move via simple diffusion. That is involved in the respiratory system, obviously, is the whole point of the respiratory system is getting oxygen in. And then what you're going to be doing is looking at how that is regulated. So without too much further ado, let's go ahead and start by talking about the types of membrane transport. So just to kind of visualize, here is our cell, here is the inside of the cell or the cytoplasm, and here is the outside of the cell out here. And obviously this is way out of proportion, but at least it's giving you some visualization of what the membrane or where the membrane can be found. And of course, eukaryotic cells are going to have more membranes on the inside. Now, if we just look at this cross section here of the membrane right here, what we see is that there are the phospholipid bilayers. So if I kind of look right here, this is all phospholipid bilayer. So we've got a phospholipid kind of being blocked by some cholesterol there, and there's two layers of it, which makes it the bilayer. We've also got those integral proteins. Here's one right there, and there's some other things that are attached to this membrane just to give you a better visualization of it. There are going to be three types of transport that you're looking at in this chapter. You're going to be looking at something called diffusion, facilitated diffusion, and osmosis. I look like you got a little smiley face in here. Let's fill that in. Anyway, in all three cases, we're going to have particles that are moving from an area of higher concentration to lower concentration. So let's start out by looking at what diffusion looks like. Diffusion happens when the particles are really, really small and they're able to fit between the phospholipids. They not only have to be small, but they need to be nonpolar because if they're polar, then they're going to be repelled by the nonpolar heads of the phospholipids. So small nonpolar chemical substances are able to diffuse or move directly across the membrane via the phospholipid bilayer. For example, let's say that I've got a really high concentration of something like oxygen You see where this is going? These guys can move right through the membrane from an area of high concentration to low. So with diffusion, what you're going to be looking at is the, this is the respiratory system. And so let's take a look here at really what's happening is we've got the lungs, so oxygen is going to come in down the trachea, down the bronchioles, and finally into the alveoli, which are the really tiny little air sacs that are here at the end. High concentration of oxygen in these areas is going to diffuse to the lower concentration that is found in the rest of the lungs. So really down the tiny little bronchioles into these air sacs. These air sacs are all, right, here's the inside of the air sac, so this would be really high concentration of oxygen lined with cells, and so that oxygen is going to have to cross these cells, cross the cells of the capillary beds, and finally make their way into the red blood cells. From there, the red blood cells are going to make their way to the heart and then out to the rest of the body, and so we've got these oxygen carrying red blood cells that eventually they get to the body cells, and oxygen is just able to diffuse right across. Okay, so that's going to be our first type of transport that you're going to be looking at. The next kind is for molecules that are either too big or that are polar. So they can't use regular simple diffusion. Instead, they're going to need some kind of help. And so we're going to call this facilitated, which just means diffusion with help. And as you can imagine, facilitated diffusion is going to need help by using channels. So these are going to have, all of your different cells are going to have different types of channels that only allow very specific, either large or polar substances through. For example, we can be looking at glucose. Glucose is a pretty large molecule compared to oxygen. It's going to be able to get into cells only if those cells have a glucose transporter. And as it turns out, most cells do, because glucose is going to be so important. Same way as we looked at with the respiratory system, we can look at the digestive system. Glucose coming into the stomach, these complex carbohydrates getting broken down into simple glucose molecules in the small intestine here, way not to scale clearly. So this would be the inside of the small intestine right here, lined by a few layers of cells, but the glucose is going to have to cross through those cells again into the capillaries and dissolve into the blood. But they're not able to get directly across the phospholipid bilayer. Instead, they're using channels to get through one side, through the other, and eventually into the blood. Okay, so that's how glucose is able to move. Finally, we're going to look at something that's a little bit different, and it's not directly the solute that's moving, but instead it is the solvent. So the last thing we're going to look at is the movement of water. Okay, so let's take a look here, and what we find is that in cases where you have solutes that are not permeable, the membrane isn't permeable to them, not permeable to whatever that solute might be. For example, a lot of times salt, certain types of sugar, sometimes large proteins. Anyway, what we find is that certain things cannot get through membranes, and so you can't really reach equilibrium by having them move. But molecules are in constant motion, and remember that we are 70-ish% water. What that means is that if the solute can't move, the solvent is going to move instead. We're going to look at some examples of this, so I don't want you to panic about it quite yet. We'll go into more detail, don't worry. But the big idea here is that when the solute cannot move, we're going to have something called osmosis, which is just the diffusion of water. or our solvent. So we've got our waters right there, but most of this is all water. So we have a higher concentration of solute up here. But we've got a higher concentration of water. Higher water concentration down below, right, in this area. And so instead of having the solute go down its concentration gradient, we're going to have the water go down its concentration gradient. In other words, from an area of high concentration of water to low concentration of water, like so. Okay, so those are the big ideas. We'll look at more specific details next week. I don't want you to stress about it. Next week, I don't know. I don't even know what day it is. We're going to roll with it. But that basically covers what the types of transport that you're going to read in this section are. Okay, so oxygen regulation, we're talking diffusion because oxygen is small, nonpolar, it's moving directly across the phospholipid bilayer. This is going to be important in the respiratory system. When we look at facilitated diffusion, we know that glucose is too big, so it's going to have to go through a channel. That makes it facilitated versus just simple diffusion, meaning that it's going through a channel instead of just through the phospholipid bilayer. We talked briefly about the digestive system. You're good there. Quick scanning, right? Nice and easy. And then finally, osmosis is all about the movement of water. Okay, but here's the thing. We talked about how they move from whatever the organ system is that's taking them in, and how they get into the circulatory system, and how they then get into the body cells. But remember in our conversation, kind of that analogy that we've been going with, if we're looking at the body like this big loop, right? And we've got all of our different organ systems, and we've got the circulatory system, we now know how everything gets from point A to point B, but we're missing two systems that we started the unit with talking about, which are going to be the nervous and the endocrine systems. Because it's not enough just to move everything around. We have to make sure it's regulated. We have to make sure that each part of the body has exactly what it needs. Too much can cause problems, too little can cause problems. You need that sweet spot. Here's where your homework comes in, is you need to look at what are the negative feedback loops for the regulation of oxygen and CO2, for glucose, and for water. And heaven forbid any of them are simple, right? Temperature was pretty simple. You get cold, your body senses cold, you do something to heat up. You get too hot, your body senses the heat, your body does something to cool down. You're going to need to read through and understand what is the regulation of oxygen, glucose, and water, and why are the stimuli what they are, because it's a little bit weird. Okay, so I'm going to set up kind of a diagram of how mentally I tend to picture this. If it is easier for you to do this in a table or to write it out as bullet points, anything is fine. But your homework is to just read through and find what are the negative feedback loops for these. In particular, I want you to be thinking about what is the stimulus, what can cause the stimulus. I should write that down. If I was smart, I would have had that written down already. So, that'll work. So, what is the stimulus? Oh, that's really big. What is the cause to that stimulus? What gets you out of homeostasis? What is the response? And why does that response work at being able to bring the body back to homeostasis? Okay, so I picture it going something like this. Again, this is how I would do it. By all means, do it whatever way works best for you. But I would be thinking about what is your set point. You don't need to necessarily find exactly what the set point is. I wouldn't expect you to memorize it other than to say the set point is whatever is normal, okay? Then I want you to look at what can cause a change? What causes a change in one direction? What kind of stimulus does that lead to? What kind of response? And what is it about that response that leads to a return to set point? On the flip side, again, what causes the change? What is the stimulus? What is the response? And why does that response get you back to your set point? You do not need to do a close read here. You do not need super detailed notes. Honestly, you'll probably be able to do a majority of the Unit 4 assessment without knowing this in too much detail. So, don't stress about it, but at the same time, if you are considering careers in healthcare or careers in anything biology related, or if you're going to be taking AP or anatomy next year, you'll probably want to have a little bit better understanding. All of that said, there's a lot of detail in this, and if this was something that I was teaching in class, we would probably spend 3 days going over it, and that includes you'd be getting homework each night, a more thorough read, more time to ask questions, and I recognize that that time isn't there. So again, try to keep it a little bit topical, and that's okay. And then if you do have more specific questions, feel free to ask. So in terms of timing wise, if you spend 10-15 minutes or so per section, you'll be in pretty good shape there. So as always, I hope you're taking care of yourselves. I miss you, totally miss the classroom dynamics we had going on, and I'll tell you right now that my 2 students that I have are cute as buttons, way cuter than you guys are, but they drive me nuts. They drive me so nuts. So I could go for someone over the age of 7 being my student again. Take care. Have a good night.